Nomenclature systems. Well, there's just some examples. So in Australia, we're different in Australia. We do everything differently down there. Of course, we've got our own system for race nomenclature. That was introduced by my predecessor, Professor Watson and Harold Lewig, who modified that original Stakeman system, the very first system that was brought in for stem race nomenclature. So we use a modified system that was developed in America many, many years ago. We have those standard differentials that Stakeman used, but then in addition to that, we've added 13 Australian differential genotypes. It's an open-ended system, so if a new resistance gene is deployed in a variety, then we will add that to the end of that set. We're up to 13 now. In Canada, back in 1963, Gordon Green, Dr. Green, developed a system that he called the C-race system. Of course, in Canada now they have adopted the North American system, what they call the North American system, the TTKS system, but this predated that. Again, Dr. Green worked in East Africa in the late 60s, early 70s, and he devised a thing called an East African system. So if you actually go back through the literature, you'll find there's some papers published by the Canadians on race analysis in East Africa from the late 60s and early 70s. They used this system they called an EA, or East African system, that used 20 differential lines. And again, it was based on 4 of the hosts that Stakeman originally identified. The North American system, this is the one that Zach took you through and I spent a little bit of time on. This is the one that seems to have been most widely adopted now, brought in by Alan Rolfs and Dr. Martins back in 1988. In India, 1986, Prasha, does that sound right? Yeah, by Dr. Nagarajan, 14 differential lines, and if we have time, it'd be really good if you could just run us through that. Sure. And in South Africa, well, Zach, back in 1988, but I think you've now supplanted that with the North American system, is that right?
Plus a few additional ones.
Plus a few additional ones.
But the earlier one was on Stakeman, right? The earlier one was based on the Stakeman differential?
Yep. Yep. So you may wonder why we use those old differentials that Stakeman found. Well, it's quite important for historical continuity. I mean, there are many reasons why we do race analysis, and I went through these the other day. One of them is long-term data sets showing long-term variation in pathogens. And you can only have that if you have differentials that you've been using over a long period of time. So some of the differential genotypes we use are not highly relevant to the wheat varieties our farmers are growing, but they're important for that in that historical context in mapping the occurrence of virulence and pathogen population dynamics over a long period of time. I don't know if I need to go through this again. How did people go? I mean, we had the exercises yesterday. I think Zach did a really, really good job with this. I think are people comfortable with the North American system now? Let's, there are 5 sets of 4 differentials, and I've got the genes here now. See, I'm not even telling you what the genotypes are. I'm just talking in terms of genes. So there are 20 differentials, 5 sets of 4, I'm sorry, and then a letter code is given depending on the response of each of those 4. So we end up with 5 letter codes, one for this, one for this, one for this, this, and this.
And the seed for those differentials comes from where?
From Dr. Eugene.
Okay.
Yeah, would be the person to get them from, I believe. So if people are interested in applying this system and they want to get seed of those differential lines, Dave, would Eugene be the best person to contact?
Yeah. He's very meticulous.
Extremely so.
About keeping these clean.
Yep. He has all the traits of a good rust pathologist and geneticist. He is incredibly meticulous, and that's what we've got to be. I mean, what would happen to me if I mixed up my SR31 differential, right, and I had the wrong thing? I somehow managed to put Morocco in my differential set instead of SR31, and of course I would find the next isolate I tested was virulent on SR31, and I made a public announcement in Australia, right? And it would be wrong. And the problem is, once you make an announcement like that, you can never get it back. So that being meticulous and being absolutely sure of your differentials is so crucial. And if you find something odd, something strange, you really have to be critical and repeat it before you tell people, before you make a public announcement. So let's just, this is probably the third or fourth time we've run through this, but let's just go through this one more time, okay? So here we have a hypothetical example of an isolate showing you what it's doing on each of those differentials. What letter code would we give for the first one here? I don't even know myself. You know, let me look at that. Sorry? Okay, next one. All right? Am I right? I might make a mistake. Tell me if I'm wrong. So what is it? High, low, high, low. High, low, high, low. So it then gets an N. Yep, people are getting ahead of me already. Next one. Yep, and the next one. So that would be pathotype FNQBR. Probably doesn't exist, I don't know. It's a hypothetical example. What would happen if I told you that I did a test and I found a pathotype that was B, 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 B? Avirulent to all of them. But I could get the same result if I had a failed inoculation. All right, so somebody sent me a stem rust isolate and it was not viable. And I inoculated the differential set and I went out and I looked at it and everything was low. I'd say, oh, it's a B, 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 B. But in fact, it's a failed inoculation. So whenever you do that, make sure you have a susceptible check in your differentials.
So maybe you'll mention it, but you can distinguish between a pathotype and a genotype?
Okay. Pathotype and genotype. This is a topic that confuses people, all right? A pathotype is simply defined, in this particular case, based on 20 genes in the pathogen genome, right? 20 genes that are conferring virulence or avirulence on those 20 resistance genes. So all we're using is 20 genes in the pathogen to characterise it. And of course stem rust has got more genes than 20. It's got lots of genes. I think the predicted number of genes in stem rust is over 2,000 based on genome sequencing. So we're only sampling 20 genes out of 2,000. All right? So we're only capturing a small amount of the variation. It's like saying, let's take a group of people and we're going to classify them based on eye colour. You can say, well, we have people with brown eyes, we have people with green eyes, we have people with blue eyes. But obviously there's variation within the people with the blue eyes. There's variation within the people with green eyes, and variation within the people with brown eyes. So we're only using a limited number of genetic traits to characterise these pathotypes. If we use genetic or DNA fingerprinting, we're using lots and lots of markers, lots of genes in the genome. That gives us an increased level of refinement in defining the genotypes, if you like. And quite often what we're finding is you can take two isolates of one pathotype, right? So they look identical on two differential sets, they look identical, and yet their genotype is different because you're looking at more than just those 20 genes conferring virulence and avirulence. Okay, so if, for example, Zach reports an FNQBR stem rust pathotype from South Africa, and I find one in Australia, that doesn't mean they're identical. Genetically, they could be completely different. All it means is that they have the same virulence and avirulence on those 20 differentials. If we do DNA fingerprinting and they're the same, then we start to become more confident that yes, they are the same thing. Is that okay, Gordon? Yep. Good. Anyway, this one, I'm not even going to go through this. Look, TTKSK, you've heard this before, right? UG99, and that's more or less what it does to the differentials when you look at it on a differential set. I think the pictures that Zach showed you yesterday were far better than the ones I'm showing you now.